So, Alfred.
Okay, so good morning, everyone. I'm Alfred Abella, and I'm here to present the generation of vortex patterns by surface waves at the liquid-gas interface. So to outline my presentation, I will first discuss experiment results on the generation of vortex structures by rotating surface waves at the liquid-gas interface. And specifically, I will describe how octupole vortices and vortex lattices are generated by progressive waves and mutually perpendicular standing waves, respectively. Then I will show a technique to obtain three-dimensional reconstructions of the surface waves and describe how velocity and vorticity fields are computed using digital particle image velocimetry. And then lastly, I will discuss how to model the wave and the vortex motion. So in previous studies, particle control via surface waves have been shown. In this work by Lukashuk et al., they controlled the motion of spherical glass spheres using surface waves, which are produced by vertically shaking the container. So as you can see in figure A, this is the initial configuration of the floating particles. And then the waves, the standing waves produced by the shaking container is seen in C, and the final configuration of the particles being trapped by the surface waves is shown in B. And in this work by Chen et al., they were able to obtain a microscale assembly directed by liquid-based template, also by shaking the container. So they controlled sampled tissues and they applied it to bioengineering applications using surface waves. So in this work by the Russian team of Filatov et al., generation of vortices by gravity waves on the water surface, they produce surface waves using these two sources, which are positioned perpendicular to each other. Then there's a camera viewing at the top. And then using tracer particles, we can see that the motion of the particles to be configured in this way, which is called the vortex lattice. And they also measure the vorticity using the data obtained from this figure A. Now, another paper by the Australian team by Francois et al. Entitled Wave-Based Liquid Interface Metamaterials. They use a similar setup. They use perpendicularly positioned paddles, which also generated surface waves on the liquid-gas interface. And then this produced the vortex lattice, similar to the Russian team. And they also observed the gyrations of the particles, as seen in this image here. They observed that the waves produced using their setup are rotating surface waves, and this provides the necessary momentum to generate these vortex lattice cells. So as you can see, the crests and the troughs of the waves rotate. This can be seen here. Now, the objectives of this presentation are to show the experiments which generate vortex patterns using surface waves at the liquid-gas interface, and to model the wave and vortex motions. So this is one of my experiment setup. So here we see a camera is placed above, which records the vortex and wave motions. And there is a speaker here which moves or oscillates the wave maker, forces the wave maker to oscillate vertically. So the tank here is 29 by 29 by 7 cm cube. And then I use tracer particles to image the vortex motion. I also placed a random dot pattern below the tank so that the wave motion can be seen. This is the octupole vortex pattern structure that can be generated using the setup. And then you can look at the upper left part. We can also see the gyrations of the particles as observed by the Australian team for their vortex lattice structure. Now to generate this pattern, we have to take note the wave maker side length, which is a square. The wave maker is a square and the side is S equals 100 millimeters. The capillary length is L sub C equal to square root of sigma over rho G, where sigma is the surface tension and rho is the density and G is 9.8 meters per second squared. And therefore, the effective vortex side length, which contains the octupole pattern, is this L effective equal to S minus 2 LC, since we have to consider the two sides. Now, the wave number of rotating waves which produce this pattern is K equals N pi over L sub F effective, where N equals 5, and the dispersion relation of the surface waves is given by this equation. The water depth is 53 millimeters, and these are the values of the surface tension, the density, and omega is equal to 2 pi F, where F is 7 hertz, set using the frequency generator. So as the wave maker oscillates, surface waves are produced, and the surface waves provide the necessary angular momentum to produce these vortex structures. So to reconstruct the wave heights produced by the wave maker, which is this, which is made of acrylic, we can make use of the deformation gradient, deformation velocity vectors produced by the perturbations on the water surface. So as you can see, this is the dot pattern, and it becomes deformed when the surface wave crests and troughs cause a lensing effect on them. So these are the deformation velocity vectors, and from these vectors, we can obtain the wave motion. We can derive the wave motion. So this is the wave motion which produces the vortex structure. We can observe that along the corners, shown by the red arrows here, the waves go in towards the center, while the black arrows point outwards towards the edges. So the motion of these waves is what produces the vortex, octupole vortex structure. Now we can decompose the right and left moving waves shown here, and then we can further decompose the waves, the right and left moving waves, so that we can see the oblique corner waves. So to produce this pattern, we need right and left moving waves, and we need oblique corner waves. Now to model the wave and vortex motion, this is the setup, where L is the crest to trough amplitude. So this is the velocity potential for a progressive surface wave, right moving progressive surface wave. Therefore, for the edge waves, we copy the same form. So this is for the left and right moving waves, and then we replace x by y for the up and down moving waves. Now for the four oblique waves, we rewrite the form of the velocity potential in this manner, where phi is equal to pi over 2 and theta equals plus minus 45 degrees. So phi is the phase difference between the oblique waves and the edge waves. So there needs to be a phase delay in order for the waves to rotate. Therefore, the velocity potential after adding up all the 8 potentials, meaning the 4 side or the 4 edge waves and the 4 oblique waves, is this, where these are the given quantities. Now, since the velocity field is just the gradient of the velocity potential, we can get this. And then we need to get the Lagrangian flow velocity or the mass transport velocity, which is in this format. But when we plug in UP in this equation, the Eulerian velocity contribution becomes 0. So we need to add an ad hoc quantity here, alpha UD, and where this is UD, or the Stokes drift velocity contribution, to take it into account the Eulerian velocity contribution. Now we can solve for U sub D using UP. So we plug in this quantity here in U sub D, and we obtain the following equations, quantities. Now, this is the result of integrating the velocity u equals alpha u sub d plus up, where alpha equals 1. As you can see, we have obtained the gyrations and the octupole vortex pattern. This is a visualization of the model. And this is a zoom in on the upper left corner. And this is a 3D render of the particle trajectories. Now, to model the waves, you have to make use of the dynamic free surface boundary condition. And then using UP obtained a while ago and linearization, we get this pattern. And then, so these are the modeled waves, wherein the waves follow the experimental results. And this is how the surface waves generate the vortex motion. Now, another experiment setup which generates the vortex lattice that I conducted the experiment. So these are the specifications of the equipment used. I use polyimide spherical particles for measurements on the water surface, and silver coated hollow glass spheres for measurements below the surface. And I use dicetyl water solution as my liquid. As you can see, we have two wave makers here powered by two speakers, and they are perpendicularly oriented with respect to each other. So this is the setup. And to image the waves, only the dot pattern is placed below the tank and the bottom LED is on. And to generate n by n cells of the vortex lattice, you have to take note of the required lambda value is equal to 2 times L effective over n, where L effective is this quantity here. And L is the side length of the wave maker, which are these two values. These are the frequency settings used for the frequency generator. Now, the surface wave visualizations using FSSS is this. As you can see, the waves are indeed rotating, and this is necessary to produce the vortex lattice cells. This is very similar to the wave pattern shown by the Australian team. Note that the wave makers are phase shifted by pi over 2. Now, if we track the motion of particles on the liquid gas interface, this is what we will see. This is for a 3x3 vortex lattice structure. And this is the final image when the video frames are stopped. So the rotating waves do generate the vortex lattice. And then I focused on the center vortex cell, which is this here, to reduce the wall friction effects. I used 2D PIV using PIVLab in MATLAB to measure the velocities of the tracer particles. I used a 64 by 64 interrogation window, and this is the result. So these are the velocity vectors. Now, to check if the particles also gyrate while drifting, as we observed a while ago for the octupole vortex structure, we have to employ a step-by-step integration scheme. And then to get the finer steps in space, we interpolate the velocity values and then before proceeding with the integration. So this is what we will get from the data. If we look at the zoom in image here, we can see the gyrations of the particles where the black dots are the starting particle positions. Now, to image the vortices below the interface, we have to make use of a laser sheet, and we illuminate every liquid layer. as you can see here. And I used silver-coated hollow glass spheres for that. So this is the speaker which forces the wave maker, which is this one. Now, side view of the setup, you can see here, the laser sheet illuminates only this particular layer. And the top view of the center vortex for using the side length L equals 100 millimeters. At depth, Z equals 3 millimeters below the interface. This is what we will see. And for Z equals 7 millimeters, this is what we'll see. So this is one vortex cell, which is located at the center of the N by N lattice. Now to model this, we again use the velocity potential for our progressive surface wave. And we superimpose orthogonal progressive surface waves with phase shift along the y-axis. And this is the total. Now, after integrating that potential, we obtain this velocity field here. And then after integrating the velocity field, you can obtain these patterns. To generate N by N cells, we have to take note of the lambda again, which is this quantity here, and the dispersion relation. And for this image here, the black dots are the random starting positions. And after integration of the velocity field, we will get these patterns. Now to model the rotating surface waves, we again make use of the dynamic free surface boundary condition. And then we obtain this eta, which is the wave height. This is the visualization of the Australian team for the surface waves producing the vortices. And these are my own visualizations. So if we place a random dot and we place parts on the surface, this is how they'll move. And then if we track their motion, we can see the vortex lattice cells. Now to summarize, I presented two vortex patterns generated by surface waves at the liquid gas interface. I visualized the wave and vortex motion using various techniques and modeled them using a potential wave approach. If you have questions or comments, please email me. And that is all. Thank you.
Okay. Thanks a lot, Alfred. So just before you leave, actually, there's a question from Perry. Why does the dot pattern have to be random?
It needs to be random because if you use a regular lattice or a regular pattern of dots, then the cross correlation algorithm might get confused. So it can associate a particular window to a different window since they look similar, even though the deformation should be just close to that particular window. So you need to have a random dot pattern.
Okay, so thanks a lot, Alfred.
Thank you.